So doctors use intravenous IV drips to deliver fluids and medications to patients. Suppose an IV drip starts with 1,000 milliliters of saline and dispenses fluid at a rate of 3.5 milliliters per minute. So the first concern I have is, in this context, is this a linear situation? Can I apply a linear model here? And I want to look for some clues in here. So we have a starts with 1,000. So we have that as an initial value. And then we have a rate that is dispensing, changing at 3.5 milliliters per minute, per meaning divide. So we do have a rate of change, and the rate of change seems to be 3.5 milliliters divided by 1 minute. And that's a fixed value. If we ignore the units per minute and we do the division, 3.5 divided by 1 is 3.5. That is a fixed number. That is our slope. So yes, this is a linear model. And the starting with 1,000, that would be our y-intercept. So we have this initial value, that starting value of 1,000 milliliters. So 1,000 is our y-intercept. So my linear model, if I were going to use, say, y for the amount of fluid, amount measured in milliliters, that's saline solution, and then x would be the number of minutes that have gone by. So again, the y is my dependent variable. It depends on time, which is independent. So I would get the equation, the fluid y is equal to the slope 3.5 times x plus 1,000. Now, right away thinking about this, I see I have a slight problem because we're starting with 1,000 and we're dispensing. I don't think I've dealt with the dispense part. What does that mean? Well, that means the bag of fluid is losing fluid. So this is actually dropping. So that should be a negative. Otherwise, if we're adding a positive amount each minute, that means we're putting fluid into the bag instead of into the person. Okay, so that's a little weird. So that should be a negative 3.5. So reading carefully, the fluid is being dispensed from the bag, so that's a drop. So starting with 1,000, we lose 3.5 milliliters per minute, and x is the number of minutes here. So we have that set up fine. A table might be a nice thing to develop here to figure out what's happening, or we could create a graphing utility. So I have x minutes, and I have y milliliters fluid. And initially, before we start draining it, so times 0, we have 1,000 milliliters. And then if 1 minute goes by, we're going to lose 3.5 mils. So that should be what, 996.5. Double check that with the calculator, or just right now, if we add 0.5, that gives us 997 plus 3 gives us 1,000. Yeah, that checks. We could jump over to 10 minutes later. What's going to happen? So we could just kind of write that out to be safe. What I would type into my calculator would be this. I think I can do this one in my head today. 10 times 3.5 would be 35, and then we take that away from 1,000. So that should be 965 mils. Double check. If we add 5, that's 70, and then 30 gives us 1,000. Okay. So we can plug in x values, number of minutes, and find the number of fluid, the amount of fluid that comes out. One thing we might want to know is when will there be no fluid? So in that case, I have to kind of reverse engineer this. So let's try that. When will the IV be empty? In other words, when will y equal 0? So we would replace the y with a 0 and then solve this equation. usual way to do this is to first get rid of the constant that's here. So I'm going to subtract 1,000 from each side. 0 minus 1,000 is negative 1,000. 1,000 minus 1,000 is 0. 0 plus negative 3.5x is negative 3.5x. And then finally we can divide here by negative 3.5 to get 1x alone. And this, I think I do want my calculator for. So we want to take our 1,000. Now both numbers are negative, and negative divided by negative is a positive, so I'm just going to type 1,000 divided by 3.5. And I get a little over, almost 286 minutes. So we're going to round to the nearest tenth, for example, here. So 285.7. And I'm going to put an approximate symbol because it's not exact. 285.7 minutes. If we wanted an exact answer, we would have to use fractions, which I don't think we need an exact answer here. It's close enough, but we should check it to make sure it's working. So if I take my original equation, negative 3.5, oops, clear, negative 3.5 times, I believe it was 285.7, and add that to 1,000. So we think this is our value for x. Plugging it into the equation gives me pretty close to 0. So there was more to that. Remember, it was 7, 1, 4 something. So since this number 285.7 is a little lower than the actual value, I'm not quite empty, but pretty close. I have 1/100th of a milliliter left, which is a very small amount. So that checked out. It's going to be, we'll have no fluid approximately 285.7 minutes later. Making a graph of that, we could use a graphing utility or just try to whip it out by hand. So let's give it a try. So we would want to get some axes in here, and then we'll roughly label them. The y-axis here is the milliliters of fluid. And the x-axis over here, that was time in minutes. And remember, it took almost 400 or almost 300 minutes, excuse me, to get no fluid. And we started off at 1,000. So I need to scale this in such a way that I can see 1,000 and I can see around 300 minutes. So what if I went 10, 20, 30, 40, 50, 60, 70, 80, 90, 100 would be up here. And actually I should have gone 100. So that would be 100, 200, 300, 400, 500, 600, 700, 800, and 1,000 would be up here near the top. Let's see, this way, maybe I'll go every 4. So 1, 2, 3, 4, that could be 100 minutes later, and then 1, 2, 3, 4, that would be 200 minutes later, and then 1, 2, 3, 4 would be 300 minutes later. So I know I started off with 1,000 at the beginning, and we're going to drop from there. And then we hit 0 at 285-ish. Is that right? 285.7, yeah. So I can't really graph a 1/10 of a unit on this scale. This would be 250 in the middle here, 275. So 285 is probably over here-ish. That's my best guess. So then roughing in this line, it looks something like that right there. And then remember, this number we started with at the top, this is our y-intercept, the 1,000. And this 285 right there, 285.7-ish, that would be our x-intercept, our horizontal intercept. How long it takes for this to end. To double check this, let's see, what else did I have? I had in my table back here, let's see if this works, the point 10,965. Let's go a little later. Let's go 100 minutes later. 100 times 3.5 would be 350, be a negative, plus 100,000, excuse me, 1,000 should give us what, 650 milliliters. That looks right. We can double check on our calculator. So I should have the point 100, 650. Let's see if I did a reasonable job. 100 should go with about 650, which, yeah, that would be right around here. Right, there's 650, here's 100. Yeah, so I did a pretty good job drawing that line. Not bad. That was a fun problem. Thanks for playing with me. Take care. Do good math.